Our first speaker is William Briggs, and in talking to him, he's my kind of guy. He figures out the statistical data on things, and I just love the statistical data. I don't know, I'm just one of those nuts where if you can't really find an answer, you just look through the statistics and you say, you know, that just can't happen. It's statistically impossible. So hopefully he'll share some great statistics on this good global warming stuff. Let's welcome William Briggs.
I guess the advantage of statistics is if you don't have any real data, you could always make it up. And speaking of that, my talk is going to be on tropical storms, hurricanes, typhoons, things like this. And I want to know what you guys think this looks like. On the x-axis down there, we have something that looks like time, and we have some numbers over there on the y-axis, 6, 8, 10, and so forth. Oh, thank you. Yes, I tend to wander. Is this working? This looks a lot like, if you've seen the hurricane numbers, it looks a lot like the hurricane plots. It looks a lot like a plot that Emmanuel published in Science, for instance, showing an increase in the number of hurricanes in the North Atlantic. Well, what this is just absolutely simulated, uncorrelated Poisson numbers. And I'll describe what I mean by Poisson numbers in a second. But these are just made-up numbers, absolutely made-up numbers. And maybe it wouldn't look that unusual, except for that little bit of an orange line I put over the top of it. And what that is a 9-year, pseudo-year running mean. These aren't real years at the bottom of the axis here. So what I want to display by this was an unfortunate tendency I see in a lot of published literature of people using incorrectly statistical methods. Now, the reason you don't want to use running means or just drawing a trend line through hurricane numbers is for two reasons. The first is it's very easy to do these simulations. You can do them just one after the other. And almost every single time you'll find somewhere in the series something that looks like a trend but is in fact not a trend. This is just completely made up data, like I said. So if you use these running mean sort of things, you're more likely to mislead yourself. The second is it's not physical. For instance, somewhere in that orange line you have something like 9.8 hurricanes estimated to be. Well, you can't have 9.8 hurricanes. You can have 8 or 9 or 10 or something like this. So it's far better to use a statistical model that is more physical. So you want something that's going to recreate the physics much better than is done using some very off-the-shelf sort of statistical modeling like you see. Okay. So this is, from 1975 to 2006, the number of tropical storms, tropical cyclones in each of 5 oceans. The North Atlantic is on the upper left, the North and South Indian are on also the top row, and the West and East Pacific are on the bottom. So what I want to do is I want to ask some questions here. I want to ask, have the number of tropical cyclones increased? One hypothesis you often hear is that with global warming, you're going to have increased sea temperatures. That follows. With increased sea temperatures, you're going to have more storms. And so one question I'm going to ask is, have there been more storms? And then I'm going to ask, well, we might even have more storms. We might have stronger storms. So I'm going to look at measures of intensity as well. So we're going to see there's going to be some problems with the Indian Ocean in particular. The reason I chose 1975 as a starting date was that was the first year at which data became widely available for each of these ocean basins. Satellites only went up in 1967. We only really began measuring well the number of tropical storms since then. So we can't go much before that. All right. Now, these are just some cartoon plots. This is the real data, but I want to be able to control for certain things in my model. The first is this thing called a cold tongue index. Now, what that is just a measure of El Nino. It's a measure of sea surface temperature near the equator in the Pacific Ocean. So as that number gets higher, we have stronger El Ninos. As it gets lower, La Ninas, and so forth. The next is this thing called a North Atlantic Oscillation Index. It's a measure of pressure, sea level pressure anomaly. We won't talk about that too much. And the last is the Atlantic Multi-Decadal Oscillation, which is an index of sea surface temperature. Now, each of these is an anomaly in some sense. That is to say, none of them displays any trend over the length of their entire series. It looks like there's a trend in the AMO right there, but that's only because I'm showing you only a small slice of it. There's no trend in any of this data, and that's important. Okay, now I'm going to show you a very scary looking thing, and I show this for the statisticians in the audience, and I'm going to step you through a little bit of it because it's important to understand the departure I'm going to make from the very simple, crude sort of statistical models to something very complex. Okay. This is complex, but let's go through this very slowly. I'm going to call the number of storms S. S for storms. Ignore everything else. And I'm going to say my uncertainty in the number of storms that are going to be next year. I don't know how many number of storms there are going to be. Could be none, could be one, could be two. I'm going to quantify that uncertainty I have using a Poisson distribution. Now that's a certain sort of probability distribution that lets me define uncertainty over discrete numbers. I can't get 1.5 storms out of this model. I can only get 1, or I can get 0 or 1 or 2 or etc. Now, the Poisson model is often used. Now, it's also indexed over 1 to 5. Those are the numbers of oceans. That's not really crucial. And the other index is over the number of years. We'll ignore that. The Poisson distribution is entirely characterized by this parameter lambda. As lambda gets bigger, we would expect to see more storms on average in any given year. As lambda gets smaller, we would expect to see fewer storms. Now that could change from year to year, and it could change due to, obviously, physical mechanisms. Interactions with El Nino or the cold tongue index, the North Atlantic Oscillation Index. Wind shear was also tried. Sea surface temperatures in the form of the AMO there. Plus this term, the second term there, you'll see I'm going to model that parameter. I'm going to take the log of lambda, that's for technical reasons, is going to be this linear function of all of these things. So in other words, I want to control for all these physical mechanisms. The second one is the important one. That's that beta 1 times t. I'm going to ask if there's a linear trend, an upward increasing trend in the mean number of storms, okay? Now, I'm using a technique called Bayesian statistics here. And Bayesian statistics is all about quantifying your uncertainty exactly. Now, I am going to estimate these beta parameters, much as you might find in a regular linear regression. But I am going to say I don't know the exact value of beta. It's going to have some uncertainty in it. After all, I'm estimating it. So my uncertainty in beta is going to itself be, I'm moving down several lines here, where it says beta and there's a straight line with a gamma and a tau. I'm going to say my uncertainty in beta is represented by a normal distribution. And that only tells me what I need to know about beta. So ignore all the rest of that. The only thing we're really interested in there is that beta 1 parameter. If we're pretty sure, 95% sure that beta 1 is positive, we could say, yes, there's been an increase in the mean number of storms. Not only do I want to do that per ocean, I want to see if there's been some sort of global, worldwide effect. And that's what that second parameter gamma is. And I'll describe it more closely when we get to the results. No, thanks. I wouldn't know how to use it. All right, so this is the same thing in cartoon. The top plot is exactly what the distribution in the number of tropical storms might look like before they happen. I don't know what they're going to be, but this describes the probability of 0, 1, 2, 3, 4, and so on. Each of these, that distribution is characterized by lambda. Lambda itself is going to be a function of all these physical components plus a possibility of a trend. And if our uncertainty in beta, if the distribution of beta that tells us, well, I don't know what the value of beta is exactly going to be. It could be exactly 0, or it could be 0.1, or 0.2, or 0.3, and there's a probability for each of those numbers. In other words, I can draw a probability distribution. If that probability distribution is mostly greater than 0, I say, yes, there's been a trend, or a good probability of a trend. If it's mostly less than 0, I say small probability of a trend. If it's been of a decrease, rather. If it's mostly around 0, I say there's no evidence for or against any kind of trend. Okay. All right. That's a lot of work just to get to this point. Now, This is the physical, this is what makes this model even more physically realistic. I'm not going to separately model the number of hurricanes. I am going to model the probability at which once a storm forms, it turns into a hurricane. So what you see here is the ratio of hurricanes in any given year divided, well, the ratio of hurricanes to storms. And for the North Atlantic, you see that's pretty constant, just under 60%. So a storm forms in the North Atlantic, there's about a 60% chance that any one of those turns into a hurricane in any given year. You can see it dramatically changes in the Indian Ocean, particularly the South Indian Ocean. And the reason for that is change in measurements. It's obvious that a hurricane definition is dependent exactly on wind speed measurements. It's got to be 65 knots or greater. And we did not measure storms in the Indian Ocean that well before, say, 1990. So it's going to look like there's been an increase in the number of storms converting to hurricanes, but only because of measurement error. So looking at it this way allows you to see that measurement error more clearly. Okay? Now, I'm not going to go through this, but all I want to, the purpose of showing this is I'm going to say the rate at which hurricanes evolve from storms itself has its own sort of a model. And again, it's in the same sort of a form. I won't describe this distribution and everything. We're just going to be looking at that beta 1 parameter, okay? And I'm going to go one step further. I'm going to say, well, a hurricane is formed. It might have the chance to develop into what we call a Category 4 or 5 storm, or in the Pacific, a super typhoon, big storm. So here we have the ratio of the Category 4 or 5 storms, super typhoons, divided by the number of hurricanes. And again, it looks like there's maybe a slight increase in the rate at which stronger storms are developing in the North Atlantic. Maybe, maybe not. We'll have to see. The North and South Indian Ocean, again, tremendous problems with wind speed measurements. And the Pacific, well, we'll talk more about that when we get to the data. Okay. Now, so I ran this model all together, all at the same time. And that's important too. I'm not trying to pick and choose separate things. So we're going to be concentrating on those dark lines first. And we're only going to look at, let's look at the North Atlantic, which is in the upper left-hand corner there. This describes the probability distribution of that beta parameter, given all of the data and the model and all that kind of thing. Remember, if most of that probability distribution is greater than 0, we could say there's been some sort of an increasing trend. Now, it looks like that solid line there says there's been pretty good probability of an increased mean number of storms. And the dotted line you see underneath of it is the same exact model, but starting from 1990. In other words, using less data. Now, I don't show you, you don't see here, but I reran this model only for the North Atlantic, and there's a paper coming out, I think this month or next month in Journal of Climate, using the data from 1967. You should use all of the data that you have available. You shouldn't pick and choose like I'm doing here, really. And if you start from 1967, no trend. The trend disappears. The reason for it is the 70s were a quiet time in the number of hurricanes. The 60s were a more average time, and it's just biasing the model. Okay. The point is, has there been an increase or a decrease in the Indian Ocean? Well, it looks like there might be a decrease. The dotted dashed line indicates 0, so maybe there's been a slight decrease in the Indian Ocean, north or south. And the Pacific Ocean, maybe nothing. Now, the overall parameter there that drives those betas in a way I never really described, centered right around 0. So what this says is there's no worldwide trend in the increasing number of tropical cyclones. And surprisingly, there's very little correlation between the number of storms in any given year between oceans. Even more surprising is that there's no real autocorrelation between the number of storms in any given ocean. That may be more surprising for anybody who knows about time series sort of things. That is to say, there's very little information in just the raw time series. You know there's going to be, if there were 10 hurricanes this year, doesn't necessarily mean there's going to be around 10 next year. It just goes right back to that original Poisson distribution. Okay. This is the same results for the probability at which hurricanes evolve from storms. Has there been an increasing trend in that? And again, mostly no, except look at the North and South Indian for the dark lines. That's the 1975 data. It looks like there has been an increasing trend in the number of hurricanes, but we saw that looks like mostly from measurement error. If we use the data from just 1990, those dotted lines, the trend disappears. In other words, that's when the data became reasonably good. And again, no worldwide phenomena. And this is the same thing for, has there been an increasing trend for the rate of strong storms, category 4 or 5 storms evolving? And same sort of thing going on with the Indian Ocean. Maybe there's something going on in the North Atlantic. That is to say, there looks like there may be some evidence of an increasing trend in very strong storms. So keep that in mind. We're going to get back to that. But nothing worldwide. This only describes the effect that the cold tongue index has. Very surprisingly, the AMO and the North Atlantic Oscillation Index had very little effect. I won't talk too much about this. It says the obvious, though. As the cold tongue index gets warmer water in the Pacific Ocean, we have more storms converting to hurricanes, more hurricanes converting to super typhoons, just as you would expect. All right. Now, a lot of work that goes on, Curry and Webster and Emanuel and so forth, they've also published things that are not like this. What they wanted to do is look at storm intensity, have storms be getting stronger. And what they generally do is they take all the storms that happen in a year, and then they come up with an index of them, some intensity index. We're going to use Emanuel's power dissipation index, and say something about the entire year as a whole. But that's the wrong way to do that. Instead, what we're going to look at is the distribution of storms within a year, okay? So what this is for each of those little things, they're box plots and maybe a little hard to see. They show the range and distribution of the number of days a storm lived in each of the years, 1975, 1976, and so on. And we're interested in, has that distribution changed through time? And it doesn't look like it's really changed too much in the North Atlantic. One possible measure, after all, of intensity is storms are living longer. They have more chance of causing more destruction. There looks like there's some discontinuities, particularly in the Indian Ocean, not surprising because of measurement error, but also in the West Pacific. We have this sort of an up and down thing. We'll get back to that. My second measure of intensity is track length. Storms could live a long time, but some of them actually just stay in place, or they circle around in a small area for a day or so. Obviously, if a storm lives longer and it moves at a greater distance, it can cause more destruction. So this is, again, the distribution of track length of individual storms within a year, okay? And lastly, this is the power dissipation index. Now, every storm has wind speed, obviously, and the stronger that wind is, the more destructive it can be. This is a mathematical representation of the power dissipation index, not potential destructive index, power dissipation index. And again, I'm looking at this for individual storms within a year, and I want to look at that distribution, okay? Now, I'm not going to show you too much of this, but I didn't want to measure any of those things independently. I'm not going to show you the model behind this. It's very complicated. But I want to look at them in a three-dimensional fashion. After all, each of these things obviously is highly correlated with each other. The longer a storm lives, the more it could track and the more power it has and so forth. So I don't want to leave any of that sort of thing out. Thank you. So I model all that together, and this thing at the bottom is called a multivariate normal, and you have to have all sorts of technical things, priors and so forth. For anybody who does know a little statistics, it's extraordinarily robust to different priors. I tried flat priors, informative priors, all sorts of priors. No matter what I did, I got the same results. That's a good sign. So here are the results. It's the same thing. They have that same form of the model. The first question asks, have the number of storm days increased? Okay? If we look from 1975, just the North Atlantic there, it looks like there's a slight probability that the number of storm days has increased per storm per year. But if we look from 1990, that dotted line there, it doesn't look like the number of storm days have increased. And again, if we look from, you're not going to see it, but if we look from 67, again, no increase. And we could look at each individual ocean. Again, we have the problems with the Indian Ocean. But the signal in the Pacific seems real. That is to say, up until about 1990, there was an increase in the number of storm days. And after that point, the number of storm days per storm went down. So that has to be explained. And worldwide, that same signal happens. All right, well, this is the, I'm going to get to the punchline here. This is the same thing for track length, almost the exact same story. And this is the same story for power dissipation index. Now, the reason this is important is because these papers in very prominent journals like Science and Nature came to the conclusion that hurricanes are getting stronger. I say that they're not getting stronger. I say something else. I'm going to show you in the next slide. This is part of that evidence. There is at least no increasing trend for the distribution of storms within a year to show increased intensity. What you do see is this. Now, I can't describe this too much, but this is the variance of those distributions, okay? So there's been no change in the mean number of storm days or mean track length or mean PDI, but the variance is increasing. And this is a solid finding. So what that means is, well, at least it's consonant with the idea that measurement has improved over time. Okay, more satellites have gone up. They've observed the storm better. They could follow the storm for a longer period of time. They do better with the wind speed measurements. These are all inverse problems sort of a thing. They're measured from the satellite. They don't know what the wind speed is. It involves some sort of algorithm that has improved through time. And so the mean hasn't changed, but the variability has, okay? And what that means is it's easier to fool yourself. If you just look at sums within a year, you're going to be more easily misled. What it looks like is happening, and this is for the number of storm days, the track length, the increasing variance, and the PDI, all the same thing. It just looks like our measurements are getting better, and we're catching more of these smaller storms. The reason it looked like there was, remember I told you long ago that maybe it looked like there was an increase in the very number of very strong storms at Category 4 and 5? Well, it turns out that the mean wind speed of storms throughout the North Atlantic and elsewhere is right around 70 knots, 69, 70 knots, which is right around the number at which you define a hurricane. So the number of hurricanes wouldn't have changed because that number was right around the mean. The mean didn't change. But you have to get up to a lot higher wind speed to define yourself as a Category 4 or 5 storm. So it looks like there's been an increase in the number of Category 4 and 5 storms, but only because we're measuring that wind speed better. We're also measuring we're measuring more smaller storms, just the ones that live for 6 hours, say. We never would have caught those before, say, 1990 or something. And again, the only thing that played was the cold tongue index. I won't get into that. So my finding is that the number of storms nor the mean intensity have increased. The variance has, and that has to do with the measurement area. The data quality is still suspect, particularly for oceans other than the North Atlantic. The West Pacific we do a pretty good job with because of Taiwan, China, and Japan, but the rest of the ocean is not so good. And it is possible to take this data and choose different starting years, and I see this happen all the time too. Well, I want to start from 1985, okay, and now all of a sudden I see an increase. Well, why are you picking 1985? You should use all of the data that you have and come up with a reasonable model for it, including the changes in the measurement capabilities and so forth. And I think that's it. Thank you.